In this problem, we want to find the response of our beam in transverse vibration that's fixed free, that's going to have a point load applied at the end for a long time, so it's going to begin at rest. We're suddenly going to remove that point load, and we want to see the vertical deflection of every point in the beam as time goes forward. So in this problem, looking at the beam, it's fixed free. We started problems like this analytically in the previous section. We were able to find the natural frequencies. For this course, though, we did not go on to find the full dynamic response of the system. We didn't look analytically at applying initial conditions and then finding the complete solution. We could analytically solve this problem in general, but that's outside the scope of this class. But how we can solve this one is numerically using finite element analysis, turning this from a continuous system into a discrete system or a multi-degree of freedom system. Once it's a multi-degree of freedom system, we're going to be able to use techniques from Unit 2 in order to find the dynamic response of the system. We can use principal coordinate analysis to see how the system is going to behave. So I'm going to outline the general steps that we want to take with this. A lot of this will be done in code there. So we want to see what each piece of the code is going to be responsible for. So in the modeling step, I won't do it on the paper, but write down the plan. We're going to use FEA, and that's going to take us from a continuous system to a multi-degree of freedom system. And that's what the mesh is doing. It's taking this infinite number of points and chunking it into these elements. And on each element we have nodes, and the nodes are what we're going to be tracking. In this case, we're going to be tracking each node's vertical deflection and the angle it makes with the horizontal. So the end result of the FEA is we're going to also apply boundary conditions, and out is going to come our M matrix and our K matrix. So the global mass matrix and the global stiffness matrix with boundary conditions applied is going to be the end result of our FEA. And at this point, it's a multi-degree of freedom system because we're going to be able to assemble then an equation of motion from this, where we're going to say that M, this matrix, times W double dot plus our K matrix times W is equal to, in this case, 0. This is a free vibrating system because the load is being applied, but as soon as the time starts, it's going to be released. So when we get to our identify step, once we assemble that equation of motion, we are going to have an MDOF system. It's going to have a lot of dimensions, as we're going to see, but it is going to be undamped. Well, we know how to handle those systems from Unit 2, and it will be free vibrating because the right-hand side is going to be 0. And this whole thing is going to be linear, the way that we are doing our finite element analysis. Since it's MDOF, undamped free vibration, we know from Unit 2 how we're going to be able to solve our system for the behavior of the degrees of freedom. So our parameter step, our natural frequencies we're going to be able to get from n inverse times k is going to give us natural frequencies, and it's going to give us our mode shapes. And that we've done before for the multi-degree of freedom systems. And we're going to be using principal coordinate analysis in order to solve for the behavior of all of our degrees of freedom. One thing to keep in mind in our equation of motion step is that this W is going to be composed of W1, W2, W3, W4, etc. But we want to keep in mind that the boundary conditions are going to eliminate some of our degrees of freedom, or that is to say, we know that those degrees of freedom are always going to be 0, so we're not going to need to solve for them. So we'll come back to this equation of motion step to remind ourselves of that. But another thing is that our odd W's are displacements or deflections, and the evens are slopes. So the way that our mesh is done from our shape function, the way that we put our degrees of freedom together, we are going to be solving all of the displacements and the slopes simultaneously. we're going to need to keep that in mind when we apply initial conditions, that we're applying the right initial conditions on the correct degrees of freedom. But we'll step back into this when we get to that point. We need to apply our ICs, so we need to know our initial displacements and slopes, like I was just talking about. And we are going to need to put these initial conditions from our original coordinate system, W, which is going to be those displacements and slopes, into our principal coordinates, Q, which we've done before. And generally that assemble step, this is where we're going to use principal coordinate analysis. So we're going to go from our principal coordinates, solving those, into solving for W. So that is, the Q is going to take us to W in that assemble step, and then we will have our full solution. And then we're going to be able to see what the behavior looks like. So this is the large roadmap that we're going to take towards solving this problem. But each of these steps we're going to be doing mostly in code, but we'll keep revisiting here to make sure that we're still on track. So let's start with the FEA step. We need to discretize this system, take it from a continuous system into a multi-degree of freedom system. And we're going to need to know how many degrees of freedom to turn it into. So part of this modeling step with the FEA is also going to be convergence testing to make sure that we are using enough elements that we are going to be capturing the actual behavior of the system, or at least the large behavior of the system, before we go in and solve it with principal components. If we're using too few degrees of freedom and we're not seeing convergence in, for example, our lower natural frequencies, our solution is not going to be good once we get to that principal coordinate analysis later. So we'll jump right into the FEA step, applying our boundary conditions and seeing what we have going on there. We've actually done this problem before in that we've done a fixed free beam in the FEA. So I can lift from that first example's code for the most part here and just put in some of the specifics for this problem. So we are given the bar radius, the length, Young's modulus, the density, and so on. So those parameters put in for this specific problem. And I do want to do convergence testing to make sure I'm going to be using enough nodes, enough elements to capture the behavior of the system. And just so that I'm really going to be careful here, I'm going to track the first 6 natural frequencies as I increase the number of elements I have to make sure that I am going to have good quality results in the end. So most of the power, and if we looked at power spectral density, we would see this, that the first 6 natural frequencies are going to encompass most of the power in the fluctuations in the system. So I'm just want to be really cautious that I'm going to get good quality results, so I'll track the first 6. Probably even tracking just the first 4 and looking for convergence would be enough, but this will make sure that we have good results. So I'm going to go up in testing from using 3 elements to using 300, and we'll see that we will get convergence definitely by 300, but we don't necessarily know that beforehand, so we will track that. All right, so for the finite element code, it's going to look like we saw in the first example here, really. The only difference is going to be I want to save out the smallest 6 natural frequencies every time I find the eigenvalues of the system. And also for this one, it's a fixed free beam. I need to apply those boundary conditions properly. So keep in mind here, the W1 and W2, the displacement at the wall and the slope at the wall respectively, are always going to be 0. Those are homogeneous boundary conditions. So an important point here is, remember in finite element analysis, I'm going to be, for homogeneous boundary conditions, eliminating 2 rows, 2 columns of K and M, and that's going to come into play in the equation of motion step, and we have to keep that in mind when we do the principal coordinates, but we'll look at that in a moment. All right, so we eliminate first row, first column of the K and the M matrices, and then we'll find the first 6 natural frequencies over and over and over again. And the first thing here is we want to make sure we're using enough elements for the next step. So we're looking for convergence of here, the first 6 natural frequencies. Again, kind of picking 6 arbitrarily, but if I converge on the first 6, I probably will have good results going forward. So let me run the FEA step, okay, and it's complete. And now visually, we're going to look for the convergence of those first 6 natural frequencies. All right, so by I here, we see that from bottom to top, the first natural frequency up to the 6th natural frequency follows the pattern that we've been seeing, is that the order of convergence is the same as the order from lowest to highest natural frequency in our system. So at least relatively here, the first 3 natural frequencies are at least relatively very flat, and they remain flat as we add more elements. The 4th natural frequency takes more elements before visually at least it's converging, and then the 5th and then the 6th takes the most elements before we see that convergence. What we do want to be careful here is the scale. So if I just zoom into, we've been tracking like the first 2 natural frequencies typically, so it is kind of tough to see here the difference because our scale is so large. But we see that the red one does take a couple of elements before it does settle into what we see in the end here. So they look flat the whole time, but part of that is the scaling. Either way, we see these flat values here, and let me just get a sense of what the first natural frequency is. So we have 444 radians per second, and the 6th natural frequency is going to converge at that higher value, 37,670 radians per second. So 300 elements is certainly enough. We could go back further. We could probably go down to 100 elements. It looks like the 6th natural frequency has converged by then, certainly, maybe even with fewer. So 100 would be fine. 300 is seemingly going to be very good for going forward on this, that it's enough that we've seen convergence. Our results after the principal coordinates should be reliable. So the finite element step was actually the easy step here because we were able to recycle code we had before for a very similar problem where we were just looking at the natural frequencies. But at this point here, we have our M and we have our K. Using 300 elements is going to be enough here. Now, when we get into our equation of motion step, this is where we need to be cautious because we have our M and our K, but keep in mind, we have already applied boundary conditions. We've already said that our W1, our W2 are going to always be 0 because that's the displacement and the slope at the wall. So actually our W at this point is not W1, 2, 3, 4, 5, 6, etc. for all of our degrees of freedom. We've actually, by crossing out the first row, first column, W1 and 2, we've already set, I have to put it in order here, 3, 4, 5, 6, etc. So W1 and 2 have already been solved. They're always 0. So the degrees of freedom we are going to be solving are going to start at W3 in this one all the way to the last degree of freedom. Keeping in mind now that W3 is the displacement of the second node to the left, and W4 is the angle of the second node to the left of the wall. So we just have to think about those things as we now apply our initial conditions as we get into using our principal coordinate analysis. So let's consider the initial conditions we have in this situation. Initially, this is a static problem, so the beam is going to adhere to our static deformation that we looked at in strength and materials and that we've been using when we were treating a beam as a 1 degree of freedom system, which is to say that if we knew the displacement at one point in the beam, we automatically know it at all points. And in the static case, that is going to be true. In the dynamic case, as we're going to be seeing when we're done with this simulation, for a beam without some point mass on it, the static assumption or treating it as a static body is not going to be very accurate. And we'll see why as we solve our principal coordinates and then get our solution back in our displacements. But initially, when it's at rest, this beam equation is good. So what we're going to use here is we're applying this load at the end of P, and remember it is going to be 50 kilonewtons as we are given in the prompt. So it's a static 50 kilonewtons. So initially, before we let go of it, the beam is assuming the shape as we have in this diagram. But our initial conditions are going to be on all of our degrees of freedom. So keep in mind here, the displacements, this is going to describe, this W and W prime are different than what we're using for our multi-degree of freedom system. In our coordinates, this is going to be our W1, W3, W5, W7, etc. These describe the odd degrees of freedom because those are the displacements. The slope initially is going to be W2, W4, W6, etc. Those are going to be all of the even degrees of freedom. So what we can do is for every value of x that we've split our beam into, so I'll draw a little bit of a very few element version of this. Now we have 300 elements, this has only 3, but the illustration is still going to pertain to here. So we're applying this load on it. So what we're going to be seeing is that these nodes initially in this cartoon are going to have some initial deflection, and that's what we are going to be tracking, is for each node how much, like at the end point here, this would be, if this is W1 and 2, 3, 4, 5, 6, so this is 7 and 8. We want to know what is W7 initially. Well, we can figure that out because we know P, and we know that each node is going to be L over, well, in this case, 3 apart. In our bigger case, each one is going to be L over 300 apart when we have the 300 elements working there. So if we know the x value for each of the nodes, we can use the static beam equation to know its initial displacement. And we can differentiate that with respect to x, and that is how we get to the initial slope for every node on the beam. So this is how we're going to be filling in the odd values of W and the even values of W for our initial conditions. Another thing to keep in mind is actually for the degrees of freedom we're solving for, we already know W1 is always 0. We already know W2 is always 0. So we're going to have to compensate for that as well when we apply these initial conditions in the code. So this is the next step. Apply our initial conditions so that we're going to be able to solve our problem using principal coordinates. So looking at our initial conditions here, I am first finding the x coordinates of every node that is in the finite element analysis that's in our mesh. So that's what this step is going to do. So x is the x location of every node. So notice the last one is at 2 because that's the length of the beam, and then going from 0 to 2, and I can do that with that lens space. P, that's our applied force at the end, so that's just going to be a constant. Now I'm going to pre-allocate my initial conditions. So I want my initial positions and my initial velocities. Because in this one we are going to be starting from rest, all of our initial velocities will be 0. And keep in mind here, when I am talking about initial position and velocity, because this W in the principal coordinates, or in our actual coordinates, W is made up of vertical displacements and angular displacements. This W0 is, again, odd values are vertical displacements, even values are the angular displacements. In the velocity, odd values are going to be linear velocities, and the even values will be angular velocities. But regardless, those are all going to be 0. The positions will not be, and that's where we have to just make sure we're putting things in the right spot. Now I want to define my initial conditions for all of my degrees of freedom. Here I am counting every node when I'm doing this, and we'll see how that changes in the next step. So del, or delta, is going to be the initial deflection, or the initial vertical displacement of every node. And here I'm using that equation from the static beam equation, the px squared over 6ei times the x minus 3l. So that's for every node, because x is representing the location of every node. That's what delta is giving us. And then theta, the initial slope of every node, that's using the x derivative of my displacement from the beam equation. So that's what I had from that picture when I was doing that handwork. So this is the initial angle at time equals 0. So these are both being caused by that static load at the end of 50 kilonewtons being applied. So when I start the timer, This is my initial position and initial angle of every node. So keep in mind, I said of every node. So the next step is I need to eliminate the nodes where, or really the degrees of freedom that are fixed to 0. In this case, it's going to be the first 2 degrees of freedom, which correspond to the first delta and the first theta. So in 97, 98, I am getting rid of the first delta and the first theta because those pertain to fixed degrees of freedom. And we'll see size-wise why that is going to be important. Notice that W0 here is the size of K, but K, and M have already been reduced by 2 when I applied the boundary conditions back in the finite element. So W0 is not including W1, W2, and W.0 is not including W1 dot, W2 dot. Those are fixed to 0. So that's important because down here in 100 and 101, I am filling in all of the odd values of my W0 with delta, and then all of the even values of W0 with theta. So this way their sizes are going to match. So let's just see the difference here in the workspace if I go step by step. So let's look at W0. W0 is only of non-fixed degrees of freedom is 600 by 1, but initially my delta value is going to be 301, and my theta is also 301 for a total of 602. So I have too many degrees of freedom, and that's why in 97, 98, I then have to eliminate the fixed ones, and now delta and theta are the right sizes. Each one is 300 for a total of 600 unknown or non-fixed degrees of freedom in my system. So I'm dwelling on this a little bit because this is certainly a confusing part of this, of making sure we're tracking only the degrees of freedom that we don't know when we go into our principal coordinate analysis. We did not have to worry about this when we were actually in Unit 2 because we didn't have to worry about fixed degrees of freedom, but now going from the finite element into our multi-degree of freedom system, that is going to be a concern. Now I can continue in the principal coordinate analysis, and from here it's going to look a lot like what we saw in Unit 2 when we used it, or what we saw when we were looking at the axial problems, because now it's a multi-degree of freedom system and it just goes into math. So I am going to go through principal coordinate analysis at this point. So I can take, using the m and the k that I was satisfied with at the end of my finite element step, which in this case were those 300 elements that made up m and k, I'm going to find the natural frequencies and the mode shapes. And here I do want all of the natural frequencies, not just the first 6. I was only testing or tracking those first 6 for convergence, but I do need to use all of them when I do principal coordinate analysis. But we know that the ones that have the most influence, those first 6 or so, are going to be very accurate as we go through this. Those higher natural frequencies are going to be inaccurate because they have probably not converged yet, but they're going to contribute so little to the solution that the error that they introduce is going to be really, really small. Right, so I find my natural frequencies, I find my mode shapes. I'm going to sort them in ascending order, which is what I typically do. I'm going to calculate my mass-normalized modal matrix just like I did before. And once I have that mass-normalized modal matrix that I'm calling it Vn here, then I can proceed further with the principal coordinate analysis. I do here as a check, just to make sure my degrees of freedom are allocated correctly, I'm going to plot my initial beam in the static position to make sure I didn't accidentally count an angle as a vertical deflection or vice versa, which again can be easy to do by accident because I'm eliminating some of my degrees of freedom that are fixed, and then I have to fill in odd values and even values. So this is just an initial check to make sure it seems to make sense. Now, this is not to scale, but what I'm really looking for here is that I don't have any discontinuities in this shape, because that would be an indication that I accidentally put like an angle in for a position. So this all looks continuous and it all looks reasonably correct for that initial position of every point in the beam. And notice what I'm plotting here. I have to stick that 0 back in for W1, which I took out during the boundary condition. And then I have, from then on, all of the odd values of my initial position, because the odd values are vertical displacements. The evens were the slopes, which I don't want to plot in this picture. So everything seems to be in line. The initial positions look to be in the right spots. So now I can proceed with principal coordinate analysis further. I now have my mass-normalized modal matrix, so I need to convert my original degrees of freedom, this W, into my principal coordinates. Right? So I'm doing this mass-normalized modal matrix inverse times my initial values, so times that W0, and that's going to give me in my Q's, my Q naughts, and then my Q dot naughts. Again, our initial velocities were all 0. The vertical velocities, our linear velocities, and our angular velocities, so that also will remain at 0. And I am going to be finding, in the end, when I go back from my principal coordinates into my original coordinate system again, I'm going to look at just 0.1 seconds of results to see what it looks like. So I'm going to, at this point, allocate my time. I can always make this longer. I can always use more time steps here, but just for illustration, I'll just track it for 1/10 of a second and 1,000 time steps in there. Now I can solve for my Q's. The whole point of the principal coordinate analysis is I'm able to decouple all of my degrees of freedom when I'm in principal coordinates. So this is the same solution we've seen before. I can use all of my natural frequencies. I can use the initial Q naughts and the Q dot naughts to get my values of Q. And finally then, I am going to go from my Q, my principal coordinate system, back into my original, because I can take that Q and I can pre-multiply by my mass-normalized modal matrix. So at this step, with 127 complete, I now have all of my degrees of freedom in my original coordinate system solved for. The evens being the angular displacements and the odds being the vertical linear displacements. But what I have to do, kind of this extra step, is I now have to put back in those degrees of freedom that were fixed, the ones that I took out all the way back here when I did my finite element analysis. When I eliminated rows and columns from K and M, I was here automatically setting W1, W2 to 0 for all points in time. So what I have to do down here in 128 is now put them back in to get back to all of the degrees of freedom, fixed and non-fixed, for my W. So I'm taking the W I just solved for. Remember, this was W3, 4, 5, 6, all the way up to W602 when I used 300 elements. So now I'm putting back in the values for W1 and W2, which, since they're fixed, are always 0, but I need to put them back in here so that W in the end is the correct size. So I'm going to go through and run all of these steps to see all the sizes that we come up with. So again, going back through, we have convergence, now doing that principal coordinate analysis step, making sure that our initial conditions looked correct, and they did. Solving for our principal coordinates, and now that step is done, and we can look at W. W now is 602 because that's the number of degrees of freedom I have when I had 300 elements by 1,000, and that 1,000 is coming from here. I was doing this for 1,000 time steps between 0 and 0.1 seconds. So playing with the degrees of freedom that are fixed is going to be really important to keep in mind, that we are taking out the correct ones. We are accommodating for them when we are applying our initial conditions at the start of our principal coordinate analysis, like I did here. I took out the ones that were always fixed. I solved for all the non-fixed ones with the principal coordinate analysis like we've done before, but then that last step is putting back in the correct places those degrees of freedom that were fixed. Again, I'll reiterate, in this problem, W1 and W2 were fixed, so those have to be put back in at the beginning, so at the right place. But for example, if I had a fixed system, I would have been taking out the first two and the last two values in W because the slope and displacement are fixed at the first node and the last node. So in that case, at this step here, I would have had to put in zeros for W1 and W2 at the front, and I would have had to put zeros in for the last two values. So I've had another set of zeros after this W to accommodate for the right wall if it were fixed. Right, so that is an extra piece we did not have to worry about when we first looked at multi-degree of freedom systems that we do now when we have these fixed boundary conditions happening. All right, so with W the right size and completely solved for, so I now know all of the displacements and all of the angular displacements at all points in time, up to a tenth of a second, and for those 1,000 time steps. Now I can plot it. So keep in mind the downside of using the finite element analysis of making a multi-degree of freedom system is that I only know the displacements of those nodes. I don't know the displacement of every point in the beam. And I don't have a closed form solution, which I would with the analytic method. But as we plot it, we're going to see that we still get a good picture of what's going on. So I'm going to plot this as an animation. So it's going to be my deflection over time. And keep in mind what I'm doing is I'm only going to plot the vertical translations. So I'm only plotting the odd values of W here, since the even are going to be the angles, which I can't really reflect well graphically. But I'm going to plot how much each node has displaced vertically at every point in time during this animation. And it's not going to be to scale, but we're going to see what the scale is once it's animated. All right, so this is highly exaggerated what we would be seeing because notice the y-axis is in millimeters, the x-axis is in meters. But we see the deflection happening here. So the tip obviously has the most, and then all the way back to the wall that has zero deflection. Now notice how the movement of the system is happening compared to if it were being treated as a static beam. We are seeing some of these extra waves happening in the beam as we go from the left side to the right side, that the static deflection equation would not be accounting for. So I'll run this another time so we can see what's happening. So there's some kind of bounce in it as we are going around. This is caused by accounting for the continuous nature of the beam rather than the simplified 1 degree of freedom version that we have been using up till now. So thinking back to in Unit 1 or Unit 2, when we had deformable beams like we have here, we said, well, we can use that static equation and treat it as though it's a 1 degree of freedom system. A 1 degree of freedom system has only one oscillation to it. It has only one frequency at which it would vibrate. But here, clearly it has more than one, and we see that because it has an infinite number of degrees of freedom. Now, when we were working, though, in the 1 degree and 2 degree of freedom systems, we did not simply have a beam oscillating. Always in that case, we had a beam, and then there was some point mass somewhere on the beam, maybe the middle, maybe the end point. And that's the difference between what we're seeing here now, where it's just the beam and it's oscillating, versus when there was a point mass on it. When there's a point mass on the beam, then it is going to typically be fair to treat it like a 1 degree of freedom system, because that point mass is usually going to be so concentrated at one point in the beam that treating it as a 1 degree of freedom system is going to be fine, because these extra oscillations, these extra degrees of freedom in the beam and its natural frequencies are going to be so overpowered by the contribution from the point mass that it is barely going to make any difference if we actually accounted for the continuous nature of the beam in those problems. So it's usually fair when we have that point mass that we don't consider the continuous nature. However, in problems like this where it's just the beam vibrating, we do need to treat it as a continuous object, because as we see here, we will get a lot of error if we were to say, you know what, it does behave as a 1 degree of freedom system, we would be missing all of these oscillations that are happening would not be reflected by treating it like the static beam equation would predict.